This is my 5th video in my Color and Light series, and it's about reflected light. And please remember to subscribe to my channel. When an incoming light ray hits a surface, it bounces off that surface so that angles A and B are equal. Think of hitting a ball to a person. You have to make the angle relatively low so he can catch it. But if you threw the ball more vertically, it would bounce up more vertically. The light seen by the viewer depends on his position relative to the reflecting surface, here the water. During sunset, the sunlight hits the water at a low angle and then reflects up to us at that same angle, so we would see the sun glare if we were standing on the beach. At noon, however, we would only see the glare of the sun if we were looking directly down at the water, since the light rays hit the water almost vertically. When light hits a glass perpendicularly, most of it is transmitted through. But if it hits the glass at less than 90 degrees, we get some reflected rays and less is transmitted through. If this angle becomes smaller, we get even more reflected rays. When we look at a lake, if our line of sight is nearly perpendicular to the water, we see its bottom. But if our line of sight makes an angle of less than 90 degrees, we see the reflection of the sky on the water that obscures our view of the bottom. This is sand with a thin layer of water on it. We see the sand in the foreground and the reflection of the sky in the background. When reflected light hits moving water, each wavelet sends light rays to our eyes, and it follows a vertical line. Yes, it wiggles a little bit this way and that way, but that's because it's hitting different parts of the wave. A viewer over here might see a vertical line in this position, but nobody should see a diagonal line. These vertical panes are reflected well because they follow this line of reflection, and we don't see reflections of the horizontal panes. To find the reflected light, identify the direction of the main light that goes from the edge of the sphere to the edge of the cast shadow. Then draw a horizontal line and find a light ray that bounces up at the same angle so that this angle equals this angle. Since direct light can't enter the cast shadow, the reflected light starts at the edges of the cast shadow and reflects in the same direction as the first one. And it gets weaker as it goes away from the ball, and you can see that this is about as far as it will go. Now, if the angle were much lower, like this one, you can see that the reflected light only occupies this part of the sphere as opposed to this part in the first ball. Since this is a white ball on a white surface, we also see tertiary reflected light. That is, the first light ray hits the ground, then hits the ball, then hits the ground again, so that this area in front of the ball is light. Similarly, when it hits the ball here, it can also lighten part of the cast shadow right here. We see tertiary reflected light here because the surface is white and the yellow is very saturated, meaning that most of the light rays coming from this bird are yellow. So the first ray goes down from his belly to his cast shadow, and then it goes up to his belly, collects some yellow light, and then goes down into the cast shadow to make this part yellow. Here are 3 white balls on white surfaces. To get the values right, I like to compare them to Photoshop scale, where white is 0% black and black is 100% black. For these 3 balls, you can see that the light area is only from 0 to 15% black. The shade is from 60 to 65% black, while the reflected light is 35 to 50% black. So you can see that the values for the reflected light are closer to the values for the shade than the light area. Reflected light requires an opaque surface, so we don't see reflected light when the ball is in the air. We also don't see reflected light if the ball is on glass. Here is the ball on a piece of paper, and we see its bottom, which is from light reflecting up from the surface. But when it's on glass, the light goes through the glass and doesn't hit the ball, so we don't see its bottom. Isn't that weird? In this first example, the light must be going in this direction because it's always perpendicular to the middle of the terminator. And look how much texture we see along the terminator. In this example, again, the light must be perpendicular to the middle of the terminator. And we see these light areas in the shaded region, which is from light hitting one egg and then reflecting to the other. My next video will be about atmospheric perspective.